Good morning, grade 10. Hope you are all doing well and being safe. This is Ms. Pamela giving the physics course. Today we are going to continue section 1 in chapter 20, which talks about the electric field. So please open your books on page 710 and follow up with me. Electric fields add together. When a system consists of several charges, the total electric field is found by superposition. That is, by calculating the vector sum of the electric fields due to the individual charges. So, in the previous session, we discussed how we can find the electric field of a single charge. Now, if we have a system that consists of several charges, we can find the total electric field due to these charges at a certain location by superposition. So, we calculate the vector sum of the electric fields due to the individual charges. So, we add the individual electric fields. This is very similar to what we did when we needed to combine the electrostatic force between several charges. Now look at the figure in front of you. In this figure, we can see two charges, Q1 and Q2. So we have an electric field due to charge 1, and we have an electric field due to charge 2. These fields are represented as vectors in black. These fields can be combined in order to find the total electric field due to both charges, which is the vector represented in red. So recall vectors addition. Whenever you want to add vectors, you add them first by drawing and then by calculation. First, I'm going to talk about the drawing part. In order to add vectors by drawing, you put the tail of the second vector on the head of the first and so on. Then you draw the resultant vector from the tail of the first to the head of the last. So the head is where the arrow is and the tail is where there's no arrow. So you have to remember this rule whenever you are adding vectors by drawing. So repeat it in your head whenever you want to draw a resultant force. You say, I put the tail of the second vector on the head of the first. Then I put the tail of the third on the head of the second, etc. until all the vectors that I want to add are done. And then I draw the resultant vector, which is the total vector, from the tail of the first to the head of the last. We will see several examples. In the figure in front of you, you can see the first two examples. They are very simple because here the vectors are on the same coordinate axis. So in part 1, they both are on the x-axis, or they both are horizontal. So we have 15 newtons to the right and 5 newtons to the left. When I superpose them and I put them above each other, the resultant force is to the right. So it is in the direction of the larger vector. If 15 newtons was to the left and 5 newtons was to the right, then the resultant vector would be to the left. So the resultant vector will be in the direction of the bigger vector. So the resultant vector here is 10 newtons to the right. Now look at part 2. Also we have two vectors that are in the same coordinate axis, which is the vertical. We have 20 newtons upwards and 3 newtons downwards. Whenever we superpose them, so we put them above each other, the resultant vector is the vector drawn from the tail of the first to the head of the last. So it is 17 newtons upwards. It is in the direction of the bigger vector, which is upwards and not downwards. If the bigger vector was downwards, then the resultant force or the resultant vector will be downwards. So we just subtract them from each other. Now in example number 3, we have one vector that is on the horizontal and one vector that is on the vertical. Here we remember the rule that I talked about. We put the tail of the second on the head of the first, and then we draw the resultant vector from the tail of the first to the head of the last. So the second vector is B. We put the tail of B on the head of A, as shown in the figure, and then I draw the resultant from the tail of A to the head of B. In number 4, I have 3 vectors, so it is more complex, but it is easy if we follow the rule. I put A, I draw it like it is, because it is the first vector. Then I bring B and I stick the tail of B to the head of A. Then I bring C and I stick the tail of C to the head of B. And the resultant vector is from the tail of the first to the head of the last, as you can see in the figure in front of you. So this is how we can find the resultant vector by drawing. Now I'm going to talk about how we can find the resultant vector by calculations. So also by calculation, we have to follow several steps in order to find the magnitude and the direction of a resultant vector. First, we find the x and y components of each vector that we need to add. Then you add the x and y components to find the x and y components of the total vector, of the resultant vector. And finally, we can find from these components the magnitude and the direction of the resultant vector. Now follow up with me so you can understand. In order to find the x and y components of a vector, we use the following equations. Rx, which is the x component, is equal to r times cosine angle. R is the magnitude of the vector and theta is the angle of the vector, the direction of the vector relative to the horizontal. Ry, which is the y component, is equal to r times sine angle. So it is the same, but the difference is that here we use sine and not cosine. R is the magnitude of the vector and theta is the angle relative to the horizontal. So in order to find the x and y components, we need to know the magnitudes of the vector, the length of the vector, which are r, which is called r, and we need to know the angle, the direction relative to the horizontal. In order to find the magnitude and the direction of the resultant vector, which will be the last step, we need to use the following equations. R, which is the magnitude, is equal to radical rx squared plus ry squared. So in order to find the magnitude of the resultant vector, we use the following equation: radical x component squared and y component squared. And in order to find the direction, which is the angle of the resultant vector, we use the following equation: tangent minus 1 is into ry over rx. So tangent minus 1 into the y component over the x component. Tangent minus 1, when we want to put it on the calculator, we put shift tangent and not tangent to the power minus 1. Shift tangent, we get minus 1, and then we put the values of the y component over the x component. In order to know the angle of each vector, you follow the rules that I stated in front of you. First, if the vector is horizontal to the right, the angle is 0 degrees. If the vector is horizontal to the left, the angle is 180 degrees. If the vector is vertical and upwards, the angle is 90 degrees. And if the vector is vertical and downwards, the angle is negative 90 degrees. If the vector has an angle other than these four angles that I just stated, the angle will be given. So the angle is either given or it will be one of these four cases. Example, find the magnitude and the direction of the total electric field at the origin due to the two charges. Q1 is equal to minus 5 microcoulombs and Q2 is equal to minus 3 microcoulombs. Q2 is 0.7 meters away from the origin and Q1 is 1.12 meters away from the origin. In order to solve such a problem, we need to follow several steps, so please concentrate with me. First, we find the magnitude of each electric field. So we find the magnitude of the individual electric field. First, we have electric field due to charge 1. Electric field due to charge 1 is equal to K times absolute value of Q1 over R squared, which is equal to 8.99 times 10 to the power 9 Newton dot meter squared per coulomb squared, this is K, times 5 times 10 to the power negative 6 coulombs. So first we do not write the sign since it is an absolute value, and we convert from microcoulombs to coulombs by multiplying by 10 to the power negative 6 over R squared, which is equal to 1.12 meters squared. This is the distance from Q1 to the origin. So the electric field due to charge 1 is equal to 35,833.86 newtons per coulomb. Then we find the electric field due to charge 2. We use the equation that you see in front of you. K times absolute value of Q2 over R squared. So it is equal to 8.99 times 10 to the power 9 Newton dot meter squared per coulomb squared, times 3 times 10 to the power negative 6 coulombs. So we convert it from microcoulombs to coulombs over 0.7 meters squared, which is the distance from Q2 to the origin. And the electric field due to charge 2 is equal to 55,040.81 newtons per coulombs. In the second step, we should draw the vectors that represent the individual electric fields at the origin. So we draw EQ1 and EQ2, as you see in the figure in front of you. Both electric fields point towards the charges since the charges are negative. So as we already know from the previous session that if a charge is negative, then the electric field points inwards towards the charge. And if the charge is positive, then the electric field points outwards, out of the charge. So here both charges are negative. This is why the vector that represents the electric field of Q1 points towards Q1, and the vector that represents the electric field of Q2 points towards Q2. The vector representing EQ2 is longer since it has a greater magnitude, as we just found in the first step. So since we calculated the individual electric fields, their magnitudes of course, we know that the electric field of charge 2 is greater in magnitude than the electric field of charge 1. This is why the vector representing the electric field of charge 2 is longer than the vector representing the electric field of charge 1. In the third step, we find the x and y components of each electric field. So first we have the electric field due to charge 1. It has a magnitude of 35,833.86 Newton per coulomb, and the angle with the horizontal is 90 degrees, since it points towards Q1, so it is upwards. So Rx is equal to R times cosine angle. R is the magnitude, and the angle is 90, and the answer is 0 Newton per coulomb. So there is no horizontal component for electric field due to charge 1. Ry is equal R times sine angle. R is 35,833.86 newtons per coulomb times sine 90, and the answer is 35,833.86 Newton per coulomb. So the vertical component is the whole magnitude of the vector, since it is on the vertical. Now we have the electric field due to charge 2. It has a magnitude of 55,040.81 newtons per coulomb, and the angle with the horizontal is 0 degrees, since it is on the horizontal pointing towards Q2. Rx is equal to R times cosine angle. So 55,040.81 Newton per coulomb times cosine 0 is equal to 55,040.81 Newton per coulomb. So all the vector is on the horizontal, and Ry is 0 Newton per coulomb. In the fourth step, we add the x and y components of the individual fields in order to find those of the total electric field. So Rx of the total electric field is equal to Rx1 plus Rx2 equals 0 plus 55,040.81 Newton per coulomb, which is equal to 55,040.81 newtons per coulomb. And Ry is equal to Ry1 plus Ry2, which is equal to 35,833.86 newtons per coulomb plus 0 newtons per coulomb. So Ry of the total electric field is equal to 35,833.86 newtons per coulomb. Now in the fifth and final step, we find the magnitude and the direction of the total electric field by drawing and by calculation. So first, to the left, we can see that we find it by drawing. We put the tail of EQ2 on the head of EQ1, and we draw the total electric field, or the vector representing the total electric field, from the tail of the first to the head of the last. So as you can see in the figure in front of you, the vector in green represents the total electric field. Now by calculation, we find the magnitude and the direction of the total electric field. R is equal to radical Rx squared plus Ry squared. We put the values, and the answer is equal to 65,677.66 newtons per coulomb. And the angle, or the direction, is equal to tangent minus 1 into Ry over Rx. So shift tangent to get tangent minus 1, and we put the magnitudes of Ry and Rx of the total electric field, and the answer is 33.06 degrees. So the total electric field due to charges Q1 and Q2 on the origin has a magnitude of 65,677.66 newtons per coulomb at an angle of 33.06 degrees to the horizontal, and we can also see it in the drawing. As a homework, please find the magnitude and direction of the total electric field at the origin due to the two charges, Q1, which is equal to positive 13 microcoulombs, and Q2, which is equal to negative 10 microcoulombs. Q1 is 2.5 meters away from the origin, Q2 is 3.1 meters away from the origin, and at an angle of 25 degrees to the horizontal. Your homeworks must be done and submitted to me on May 12, Tuesday. Thank you, good luck, and stay safe.